Hello everybody, it's Mrs. Avon. In Chapter 3, we studied how an object moves, how far it moves, its displacement, how fast it moves, its velocity, how much its velocity is changing when we looked at acceleration. When we look at why an object moves, we can answer that question with one simple word: forces. A force is a push or a pull. That's a very basic definition for a force. And when objects are interacting, forces exist. We can classify forces into two types: a contact force, which requires physical touching between two objects, and a field, or sometimes they call it action at a distance force, which is exerted without contact. So an example of a contact force would be friction. An example of a field force would be gravity, and we have already started to study gravity by looking at free fall in Chapter 3. We're going to start our study of forces in much the same way. We're going to look at what we call a free body diagram. That's what capital F, capital B, capital D means, a free body diagram. And it simply is going to look at the individual forces that are acting on an object. So when we draw a free body diagram, the object can be a box, it could be a circle, it doesn't really matter what you use, but typically you'll see on the physics classroom and in class using a box, and the arrows represent the forces. And the length of the arrows would represent the magnitude of the force, and the direction that the arrowhead points represents the direction of the force. And we don't typically study individual forces. We look at the result of multiple forces that are acting on an object, and we call that the net force. So the first thing that we have to do to understand forces is to first be able to identify them and then be able to determine F net. So when we look at a typical free body diagram, the one on the left, you see F tends upward, that means tension, and you see F grav down, that's gravity, two of the forces listed in your textbook. If F tension is 1200 newtons up and F grav is 800 newtons down, the net force would just be found by subtracting the two. They're vectors and they're in opposite directions. So if you look, F net is 400 newtons up. The second picture, F air, is 600 newtons up and F grav is 800 newtons down. We simply subtract them, just like we did in previous chapters. So the net force is going to be 200 newtons down. If we have forces that are both in the vertical direction, which we're going to call the y, and in the horizontal direction that we call the x, you can see we have F normal and F grav balancing each other out, both at 50 newtons, and we only have F friction in the x direction, which is 20 newtons to the left. So it's very simple to identify the net force. You simply take the forces in one dimension, either x or y, and you subtract them. The net force is going to be in the same direction as the larger force. So we're still dealing with vectors, and when they're in opposite directions, we can simply subtract them. When we look at how forces behave, they behave according to Newton's three laws, and we're going to begin by examining the first two laws. And as I said before, it's very important that you identify the net force, because Newton's first two laws are going to look at when the forces are balanced and there is zero net force, and when the forces are unbalanced and there is a net force, and that's going to give us some very important information about the motion of the object. So Newton's first law, you can find it completely written out in your textbook. This is just a summary. So Newton's first law says an object in motion stays in motion, and an object at rest stays at rest. And this situation will continue to occur, either the object in motion or at rest, unless there is an unbalanced force acting on the object. So the physics classroom has a very nice graphic. There are two options when looking at Newton's first law. If the forces are balanced, the object can either be at rest with a velocity of 0 and stay at rest, or the object can be in motion and stay in motion in the same speed and in the same direction. So when we look, most importantly about the commonality between these two situations is that they both have zero acceleration. So Newton's first law is referring to situations where we have zero acceleration, whether we're at rest or we're in motion. So when we talk about Newton's first law, it is typically abbreviated or also known as the law of inertia. And inertia is the tendency of an object to resist changes in motion or resist changes in velocity. That's another way to say the same thing. It is very important that you understand that inertia is not a force. I'm going to say that again so you write it down. Inertia is not a force. It is just a tendency of an object to resist changes in its motion. And it is measured by one thing, and that is mass. So if you have two identical objects in size and shape, but one has a greater mass, it's going to have a greater inertia. It's just a property of an object that is measured simply by its mass. Now, it wasn't Newton, because these are Newton's three laws of motion, if I didn't say that before. It was Galileo who developed the concept of inertia, but it was Newton that sort of added to it. And Galileo simply said that if friction could be eliminated, you could take a ball and roll it in a small distance, like a U shape, and it would attain its original height. Even if you change the U shape to stretch it out, it would again attain its original height. So he said if friction could be eliminated, when you drop that ball or roll that ball down the incline, it's never going to stop rolling. So Galileo actually developed the concept of inertia, but Newton took it one step further and said that a force is not needed to keep an object in motion. And that is sort of an application of Newton's first law that very often gets overlooked. A force is not needed to keep an object in motion. If it's in motion, it stays in motion. A force does not need to be applied to keep it in that motion. So when we look at Newton's first law, we remember that it is abbreviated with the word inertia. If you can remember what that means, it will help you remember Newton's first law. And that it deals with objects that have balanced forces that are not accelerating. So when we look at a free body diagram, we know that an object is in equilibrium. That's another way to say that the forces are balanced. And that object does not accelerate when the vectors opposite each other are the same length. So object C is in equilibrium both vertically and horizontally. So I know that object C is either moving with a constant speed or velocity, or it's at rest. Object H has balanced forces vertically, so it either has to be at rest or moving at a constant velocity. It's very important to understand that free body diagrams do not show you the direction of motion. They simply tell you whether or not the forces are balanced, and therefore whether or not the object is accelerating. And when an object is accelerating, we will look at Newton's second law to tell us how much that object is accelerating. So Newton's first law dealt with balanced forces. When they're balanced, the acceleration is zero, and the object is either at rest or moving with a constant velocity. Newton's second law deals with unbalanced forces. And if a balanced force has zero acceleration, an unbalanced force, there is an acceleration. So when we look at Newton's second law, it is basically the only mathematical law. We can sort of apply some math to Newton's third law, which is action-reaction, that we'll talk about later. But the one that we use the most in this chapter is Newton's second law, which says that the acceleration depends directly upon the net force and inversely upon the mass. And that is just a way to state the equations to the right of this slide. F net equals mass times acceleration. Or you can rewrite the same equation, just rearrange it, that says A is equal to F net divided by M, and that's where we get the directly related to the net force, because they're both in the numerator, and inversely related to the mass, because acceleration is in the numerator, mass is in the denominator. And as I said earlier, it's very important to be able to identify the net force, because that will tell us about the acceleration of the object. Again, when we look at free body diagrams, the forces in the opposite directions are not equal when the forces are unbalanced, and that means that the object is accelerating. So letter G is going to be accelerating in the down direction because the net force is in the down direction. Object B, there's no acceleration vertically because those vectors are equal, but it is accelerating to the left, or its acceleration is to the left. It's very important when you look at these free body diagrams to understand what they tell you and what they don't tell you. They do not tell you the direction of motion. So you're going to see various pictures of free body diagrams. When we look at the various free body diagrams in this picture, A through J, it's very important that you understand A. The only thing I know about A from this free body diagram is that its acceleration is downward. I don't know which direction it's moving. Same for B through J for all of them. So B could be moving to the right. If it were moving to the right, its acceleration is to the left, therefore it would be slowing down. B could also be moving to the left. If it were moving to the left, that means it's speeding up. So when you look at pictures of free body diagrams, they only tell you the direction of the acceleration, the direction of the net force. We would have to be given the direction of motion in order to tell whether the object was speeding up or slowing down. So we're going to take a look at free body diagrams over the next couple days and look at how we can analyze the motion of an object, particularly its acceleration, through these pictures.
Go where you want to. Do the things you feel. Walk around with a broken leg and $100 bill. Get yourself a pistol. Get yourself a dog.